OSC Systems Tour. I think you would have got the emails. So 5 o'clock, I think Matt will be leading all of you. So let's go through two short talks. Today we have two. Tomorrow I think we have 4 or 5. So these are, as I said, like some of the upcoming work, whatever is coming. So that I hinted at some of these things in my roadmap talks also. So some of these designs will actually be appearing in the MAPH and HPCI releases in the near future. So we'll have two presentations. So first it will be by Lang, and then the second one is by Sanjay. So Lang is a PhD student. His research interests include high performance networking, distributed deep learning, especially large model training and inferencing. He has published papers in major conferences like CCGrid, IPC, IPDPS, etc. He is focusing on communication and networking strategies to enable efficient large-scale ML systems. He actively contributes to the MAPH library, and the HiDL is the older name of the HPCI project. And the next one, Swangjae, he actually joined us from Kookmin University in Seoul, South Korea, where he received a master's degree. So currently he's working on the MAPH project. His research interests include efficient network communication for HPC, in-network computing, and automated tuning. And he will be talking about that AI for MPI. I remember I mentioned that. How do you take care of the collective tuning? So let's get started with Lang, and then we'll switch to Sanjay.
All right. This short talk will be an introduction and overview on communication patterns and the distributed large language model inference. So the problem statements that we want to address here is that the first one is what are the predominant types, volumes, and patterns of communication during multi-GPU deployment when you are doing inference for large language models? And can we derive or develop analytical models to predict such communication with certain parameters? We are considering parallelism degree. We are considering model architectures and such. What is the impact of communication patterns when it comes to user-facing metrics, service level objectives? Given a set of resources, what is the comparative impact of different parallelism layout? Okay. We'll be going through several analytical models. We'll be covering communication volumes across different parallelism layout, across tensor, pipeline, hybrid parallelism, and we'll base our studies, scope it onto VLM framework and Llama-based dense transform architectures. So this is kind of like a term table for you to refer later on when we're talking about some formulas and communication volumes. So the first one we get touched, which is the most famous one, I think it's tensor parallelism. A lot of people use this parallelism to scale within a node. It is basically a distributed matrix multiplications across GPUs. So within each transformer block, there will be 2 layers, and for each layer, they will be calling one RReduce. So within each transformer block, there will be 2 RReduce at a measure size of they are passing around hidden states. So it's H elements. A brief overview, a brief intuition on that is that you first shard it on the row parallelism layer, and it partition on the row layer, and then row dimension, and then you partition the second on the COM layer. So there's no additional all gather within it. So typically there will be 2 RReduce layer per transformer block. And when we look at VLM framework, we realize that there will be another 1 RReduce at the embedding layer per token. There will be also a final gather on the final logic computations because we are passing out sharded parts of the final logics, and the root rank will be gathering all the logics to spit out the output tokens. So the formula here is that you have 2 times L, you have 2 RReduces per layer, you have 1 additional at the embedding layer, and you have the prefill sequences, and you have decode sequences -1. That's because you already processed through 1 token at the prefill stage. And then you will time it by the hidden size, time it by the bytes per element. For bflow 16, that's 2. FP8, that would be 1. And then you time it by doing a bus bandwidth factor. So basically, we assume the R reduce here is a ring R reduce. That will be a 1 reduced gather followed by the all gather. There will be, for each part of this collective, there will be T minus 1, which is the tensor parallel size hops for each of these collectives. And we divide it by the number of ranks. That's the per GPU volume. And then the final one is the gather volume term. And for pipeline parallelisms, we have, basically we shard different layers. We do like an interlayer sharding. We have different layers on different GPUs, and they will be sending and receiving activations. For this dense model, we also need to send and receive the residual connections. So basically, the volume here indicates that we have, for example, like four GPUs holding subset of layers. We have 3 links. We'll be communicating residuals and activations that the factor of 2 here, and then we'll be processing it through every token. So 1 token for the prefill stage and the subsequent decoding tokens. For hybrid parallelism, it will be a combination of several things. We will have all reduce, all gather, gather, and point-to-point. So the all reduce, we have a reduced factor of P because we are not for each GPU, we are not calling as much all reduce as for pure tensor parallelism. We have the gather for the largest at the end, as always. We also have the all gather because for pipeline stages, we are sending sharded activations and residuals to the next stage. So we need an all gather at each next stage GPU to actually continually perform the TP domain. For point-to-point, this is on a per GPU basis because for each GPU, they will be only sending its activations and residuals. It doesn't relate to the number of links. So there are also some the experimental setup. The study is conducted on the Cardinal system. We have 4 NVIDIA H100s. We have a 4 NICs per node, and they are 400 gigabits per second. The software package a little bit out of date. It's based on PyTorch 2.6, VLM 0.8.5, Post1 V0 engine. And we also have Nickel 2.21.5 as the communication stack. We conduct some validations on different dense models, 3 billion, 8 billion, 13 billion llama models. We restrict we are trying to scope down the complexity a little bit. So we force it to be a 1 batch size. We use PyTorch profiler. At that time, we also use the VLM RESTful observability API for profiling. Okay. We'll be looking at some communication volumes. As you see, for different models, tensor parallelism will have the most communication overhead because that scales with model size and sequence length, and it's also dependent on the number of layers. Pipeline parallelism has the minimal pressure on network. It is good for bandwidth constrained and long sequence scenarios. But it is significantly underutilizing the GPU compute because you need to spit out tokens after each other. Hybrid parallelism strikes a balance between communication overhead and GPU utilizations. You have the middle communication volume here between tensor and the pipeline. So there are also some performance analysis on the SLO evaluations. The first one is the pure TP configurations. For time to first output token, it is really compute heavy because we are doing 1 prefill with a large matrix sizes. It improves as we increase the TP degree because we are dividing the workloads among the GPUs. For TPOD, which is time per output token, it is more memory bound because we are only outputting 1 token after each other. In this graph, the TP8 has significantly higher TPOD because it's crossed the internode boundary. That'll make things worse. And we also looked at pipeline parallelism. So pipeline parallelism, it has data dependency and its latency scales with the number of links. As usual, PP equals 8. It crosses node boundaries, expose the internode connections in the hot path. The time TTFT is significantly increases. TPOD is memory bound. It is increased and it's dominated by the critical links here. It has larger latency here. Okay, some conclusions at the end of the time limit here. So inference workloads impose some communications with moderate message sizes and high frequencies, and decode stage is more memory bound. It dominates communication frequencies. So basically, if you're doing tensor parallelism, you have pipeline parallelism. All-reduced and point-to-point communications are the two major primitives in these parallelism layouts. Tensor parallelism has better GPU utilizations because it can divide large matrices among GPUs, but it has substantial communication overhead because if you go through every layer, you have to go through every layer and you have to do like twice per layer. So if it's like latency sensitive and short generation tasks, you don't really want it to generate a lot of tokens because per tokens, you also have to call or reduce a lot. Pipeline parallelism offers a minimal communication overhead because it's also depends on the number of links, but however, it has low GPU utilizations if you don't have a good overlap with the compute because it will have a dependency, it will have a bubble in the timeline, which is detrimental to latency, specifically TPOP where it is memory bound. So final conclusion is that while computation parallelizations can overcome communication overhead for short sequences, it diminishes with longer sequence and internal deployments. We really want to scale. So looking at your topology depends on how much bandwidth you have for each different tier of your topologies. You will apply different parallelisms when you're trying to do LLM inference. So a final thank you for all your attentions. And this is a previous effort on the HPC AI project. Thanks.
Any quick question? One question we can take there. Okay, if not Sanjay, let's continue. I think.
Okay. Hi everyone. I'm Sungjae. Today I'll be present our machine learning based MPI tuning, head MPI hierarchical auto tuning of MPI internode communication on InfiniBand clusters. This paper actually did at HBT workshop, and today I'll present this paper. This is the outline of this paper. I will start with the motivation and the problem statement. So as you know, InfiniBand clusters are one of the major types of HPC clusters. You can run applications like LLM training or HPC applications with communication middleware such as MPI and UCX. And when you use these middlewares, you need to optimize them to get better performance. But it's actually difficult to find the optimal configuration due to the wide variety of hardware configurations and tunable parameters. as Dr. Panda mentioned, there are more than 200 parameters in MPI. So our motivation is this: how can we optimize hierarchical HPC middlewares with minimal benchmarking? So can we use machine learning based modeling to solve this problem? So one of the most important parameters on UCX is the Igor roundup threshold. So UCX provides various protocols, but the biggest performance gap is coming from threshold between Igor and roundup threshold. Another important parameter we can consider is MPI collective algorithm selection. So MPI basically provides various algorithms for each collective operation. For example, MPICH has a blocks, non-blocking, pairwise scattered, and some other ortho algorithms. So selecting one optimal algorithm for a given cluster, scale, message size is actually very difficult. There are some existing solutions, for example, exhaustive searching, but it consumes a lot of node hours and human effort. There are some other previous studies with machine learning based solutions, but they're also limited to a specific software layer. So they don't much consider about hierarchical characteristics. So in this work, we propose machine learning based auto tuning consider both UCX and MPI layer parameters. So we call this hierarchical auto tuning hat MPI, and I will introduce our design of this framework. So this is our design of hat MPI framework. It has three major components in here. First one is a LLM-assisted hardware feature collector, which is a data collection part. Second one is modeling for UCX Igor roundup threshold and also MPI collective algorithm selection. And lastly, we also use the spatial evaluation method. For data collection, so as you know, data is like fundamental for machine learning modeling. So we collected hardware features from all the InfiniBand clusters from various HPC systems. And also we measure OMB benchmark latency for model training. For the modeling, we have two separate machine learning models. So one is the UCX threshold prediction model, and the other one is the MPI algorithm latency predictor. So the UCX threshold model uses hardware features we collected from first box. We use that hardware features to predict optimal UCX threshold for a given cluster. The MPI algorithm latency model, they use hardware features, runtime parameters, and the predicted UCX threshold from the previous model. So we build one model for each collective types. This predicts the algorithm latencies for the collective operation, and then we can choose the optimal algorithm in that collective operation. Third one is the evaluation method. We mentioned about the evaluation here. I will explain in the next slide. So hat MPI basically has two major evaluation methods. First one is the leave one system out method. As we are trying to predict and optimize for an unseen InfiniBand cluster, so we separate systems data from one system's data from others. So we can use that specific data set as a test data set, so we can be we can do more fair evaluation, something similar to the real world scenario. Secondly, we developed a new evaluation method, which is called top 5% accuracy. So if you have some experience in MPI tuning, We often see several algorithms are showing almost the same performance. For example, if you see that this is some kind of example case, Brog is showing 100 microseconds and pairwise is showing 105 microseconds, which is almost same. So we believe that only considering the single best algorithm as the correct answer is not a good approach in this case. So with 5%, top 5% accuracy metric, we also consider other algorithms that fall within a 5% gap, 5% gap of the best performing algorithm. So in this case, Brooks and pairwise both gonna be the correct answer. Now I want to show performance evaluation results. Before we actually go into the evaluation numbers, here's the experimental configuration. So we carefully selected the overall cluster size and scale, and we collected the data from different CPU vendors and network types. So we collected data set from HPCAG, OSC, and TAC systems. And I really appreciate for all of these supercomputer centers for providing access and support. On the top of those InfiniBand clusters, we use the latest UCX 1.20.0 and also use the EMBA-Pitch Plus for algorithm modeling. So we are focusing on Ortur and Origus collectives in this work. We evaluate HatMPI's prediction accuracy for Ortur and Origus. So these figures show top 1 accuracy with blue bars and top 5% accuracy with orange bars. For Ortur, left figure is the top 1 accuracy is around the 60 to 70%, and the top 5% accuracy is around 80 to 90%. There's a pretty big gap between blue bars and orange bars, which means several algorithms show similar performance, and the top 5% accuracy effectively captures this, and showing that we can achieve very good prediction accuracy without hurting performance that much. So if you move to the right figure, that's the Origus result. So we also can see the similar pattern, a little different from the previous one. It has a actually bigger gap compared to the Ortur case. So I think that means it has more algorithms with similar performance, and that hurts top 1 accuracy much more than Ortur case. So for the top 5% accuracy in Origus case, it is even higher than before. It is almost close to 95%, which means HatMPI is predicting algorithms with very high accuracy. So lastly, I want to cover conclusion and future work of this work. So we introduced the HatMPI, which is a hierarchical auto-tuning framework. We model UCX Igor rounded threshold and also MPI collective algorithm selection. Our experiment shows that HatMPI can achieve up to 90 to 95% of accuracy in collective algorithm selection with UCX Igor rounded threshold modeling. About our future work plan, we want to extend HatMPI to more other collective types. We want to do more comparative evaluation with other frameworks. We're also trying to develop zero overhead prediction model with that LLM assisted feature collector. And finally, we want to integrate this framework into the EMBA-Pitch Plus so we can automatically optimize for any systems with the hardware features. That is our final goal. Thank you for listening. If you have any questions, please let me know.
Thanks to Sanjay. Any quick questions? Yeah, Jitin.
Maybe one key question. So what could be the reasoning behind the top 5 getting better accuracy than the top 1?
Your question is, what's the difference between top 1 and top 5?
Oh, what's the reasoning behind top 5 getting better accuracy as compared to the top 1?
You mean the reason of why top 5% is has a better accuracy than top 1? That is actually very simple, because top 1 is only considering the only one algorithm as an answer. But if you extend the answer sheet to top 5%, there can be 2 correct answers. So even my framework predicts pairwise as a correct answer, that's also correct. But it's not correct if you consider the top 1 metric.
I see. So it doesn't map directly to the performance. It's actually the accuracy of the prediction. Is that correct?
Oh, yes, that's correct.
Okay, any other question, Sanjay? Okay, so if not, we'll almost finish the event for today. We have this, we keep some time for open mic session. I know we discuss offline, but anybody has any open questions, comments, thoughts, feedback, this is the right time. Anybody in general, MFH project, HPCI project?